So the last time I was running the convolution uh, with this resonate architecture, I ended up printing some of this model structure, right? And that time I noticed this, and right now, sometime back while I was running that uh, YOLO experiment with TensorFlow and for you know deep sort, following the AI guys, right? So what we got to see here, total params, trainable params, non-trainable params. This is coming from TensorFlow and Keras, and this what I have here is coming from uh, this is coming from the resonate architecture, but not of nothing to do with the TensorFlow or Keras over here, is what I'm presuming. This is PyTorch, right? So again, it is the same structure: total params, trainable params. And why? Because seems people have been trying very much to get that Keras and that TensorFlow format summary out here, right? And because of which this is what we are getting. So, and where is this code of mine? So this code is again something experimental I've been doing earlier, and yeah, this is where it is. And I had uh, what I remember is I got one specific library in here. I think something info or something uh, to get this and print this, and then later on, in place of just using that library, I ended up uh, you know doing a simple print of the model, and there itself I seemingly got uh, good results, in the sense I got a decent enough representation of the model architecture over there. mm, so I don't necessarily remember which one is that. Anyway, I'll come back to that when I remember that. uh, I think this one which is there, uh, which I think starts off from here, downwards, is from that particular library. And so it says convolution 2D, then batch norm, then ReLU, then max pool, and then sequential. And then within sequential, there are these, basic block. And then I think this is the second sequential. And then there is this block structure. But what you get to see down here is the normal print, which is this. Yeah. So one second. Yeah. So this is just printing the model. Yeah. So that one is torch info import summary. Yeah, torch info is what I was looking for, that info library. So I had to uh, get this in separately. Okay. Now, so this is the conv 2D layer. Uh, what are these values? So to understand these values, I've made some notes up here. I'll just quickly go through those notes. The first is the in channel. How many channels is the input? So if it is RGB input, they call it image volume or input, then you will have three channels over here. So this is this is what I've written: count of input channels in this convolution layer. So RGB would be there. So this is the raw image input channels. And then what is the out channels, which is this, the second value. So count of output channels in this convolution layer. And then what is the kernel size? So 7 by 7 is the height and width of the filter that is being used in this layer. And then what is the stride? So stride is obviously how the convolution kernel is moving, right? As an example, I would have come here later, but this is what the stride is all about, right? So, so this is no padding, no strides. Padding would be that you got zeros around the entire thing, but there is no padding. So this is arbitrary padding, no strides. In the sense, when you say there is no stride, it is moving one block after the next block after the next block in a continuous manner. It is not necessarily uh, jumping around, right? And this is padding and strides. This is no padding but strides. So I think this stride is 2 because when it moves from one position to the other, you can see it is jumping over 2. So I think this stride, even though they've not written it, is 2 by 2. And this actually is recommended for this dilation. For dilation, a lot of people are saying that, go to this particular README and have a look over there. So dilation is what is recommended over here. But the rest of it, if you see, of course, makes a lot of sense. So coming back to my notes, now that is a stride. So move right and across, also 2 down. So move right 2 and across also 2. Sorry, right oblique across. So move right oblique across and then move 2 down. So that is 2 by 2. And if the stride is 2, then the feature map is half times the size of the input. If the stride is 1, then the feature map is same, 1 times the same size of the input. And then constraints on strides. So this I need to, I put a to do over there. I need to further put some notes over here. Note again that the spatial arrangement hyperparameters have mutual constraints. Uh, what I remember and what I had read, and I need to kind of document that, is that you can't necessarily have a stride which will be like say a 3 by 3 or something, and then not have a padding. So you probably will go off the image if that is the way you're convolving over the image. So that is one thing which can be there. So that is why it says have mutual constraints. So when this stride and these things are calculated, uh, they mutually constrain each other. So there are certain rules that they have to follow. Otherwise, it will not work. It will fail. Okay. Then comes the padding. The padding. So height and sorry, width. It has to be width. I'm sorry. Yeah, height into width. So pad with 3 zeros. In case the stride makes the filter go outside of the tensor window. So if your stride has to be such that you have to go outside the existing window, then you can pad with zeros, and then accordingly your stride will not escape the entire image. It will not escape the padded image. It will remain within the padded image. Okay, then batch normalization, exploding or vanishing gradients may still happen even though we did a transform normalize. Okay, so within our transforms, the transforms that we have composed and we have got those transforms, within our code, uh, how we need to understand that is that let's say these are transforms for the resonate, right? So the mean and the standard deviation over here. Okay, the mean and the standard deviation. Uh, but there could be a certain situation, especially in the resonates case, being a very very deep network, things might still go wrong. That the overall transformation that you have done, that impact might not remain. So that's the reason you introduce this particular layer. So even though you've done that, still you have a batch normalization layer, right? And which one is this? This is what you get to see down here, the BN1, and similarly there can be more than one instance of this batch normalization layer. And these are the parameters: 64 EPS, momentum, affine true, tracking status true. So how do we understand these? To understand these, it is best to head off to the official documentation. But I still need to understand more on this, so I'll come back to this. This I still have some questions over here. Okay. So again, these are some references that I need to read through. Then MaxPool 2D. So what exactly is this layer doing? And this layer is the third one in the occurrence over here. Sorry, the fourth one in the occurrence over here. And what exactly is this doing? So what is kernel size? What is stride? What is padding? The stride padding we've understood up there. What is dilation? Dilation, again, this is what the dilation is, right? And then seal mode. Now the seal mode false I have been kind of struggling to understand, but of course it's PyTorch and it is quite similar to NumPy. So I presume that you are taking the floats and sealing the decimal point is what I understand to make the input or the tensors maybe uh, making them more accurate and less sparse or something of that sort is what I understand. Yeah, because ultimately the aim of this max pool two-dimensional layer is to reduce the resolution of the input images, right? Compress the input volume. So if you want to compress things, you probably don't want sparse data, and uh, data which is previous to the seal uh, could be considered as I don't know, maybe sparse data or too verbose data. I really don't know. I'll have to check this. Right. So yeah. Mm, so this is what I have gone through, and rest of it, of course, I need to go through this again. And uh, torch summary, and this summary is what you really need to print out and understand so that you understand the structure of your neural net, and then you can play around with these layers. In the sense, you can drop certain layers. You will have to freeze certain layers and freeze certain weights to make sure they are not part of your net, and then training can be faster, inference can be faster. You probably don't need for all your use cases all of these layers, right? So many parameters and all of this is not probably required. All of this might not be required for each and every use case, is what is the learning from here. So here is that concept of freezing certain layers. So certain parts of the uh, network which are not required, you end up freezing them. So he says I want to set some of my model uh, frozen. So how to do that, right? And this is a wonderful explanation over here, and let's upvote it. If you want to freeze part of your model and train the rest, you can set requires grad of the parameters you want to freeze to false. For example, if you only want to keep the convolution part of VGG16 fixed, then model is a torch vision models pre-trained. Okay, so that is how you would get the model in. And for model features parameters, okay, model features and then parameters, okay, yeah. So you freeze that. Okay. By switching the required grad flag to false, no intermediate buffers will be saved until the computation gets to some point where one of the inputs of the operation requires the gradient. Okay. And I think torch no grad and this requires grad equal to false will run in tandem. So this has to probably be in, requires grad true. Okay. Then, yeah. So this is how we can end up using some parts of the model and not use the entire model. So for something like ResNet, you don't necessarily want to go through the entire thing, right? There are too many layers. So some of these layers we can freeze. But it is recommended that you don't end up freezing the batch normalization layers because those would still be required. Yeah. So obviously this is, I think this is to be noted that in case we don't want to fine tune, the goal is not to fine tune the or not to selectively choose the layers of the neural net, and you just want to put the model in evaluation mode. So obviously model.eval is the way to go. So model.eval, so that's been happening a couple of times, so that is okay. uh, right? So that is okay. But freezing the gradients is something which needs to be understood very well as to which ones you would want to freeze and why, right? So, okay. So now to continue with what I was trying to do earlier. So here is a bit of code that I was using earlier also for airplane and not plane that I had, and I was running that. Now what do I have here is some glass images. Yeah. So lots of glass images and not glass images, right? So of course those earlier images of faces that I've been using, I'm using them here also. Okay, now this is the setup, and the code is again, you know, that SimpleNet which I had done earlier. So this is the simplest possible with PyTorch, and it is giving me a pretty decent accuracy. So when I run this, there is nothing much which is happening, right? So there's a resize which is happening in the transforms. We are doing a two tensor, then the normalize is the same resnet normalize, this mean and standard deviation. Uh, then there are these linear layers, and when I'm printing out the model, which I'm yeah, the summary, so we can see over here how this is structured, right? So in features, out features, in features, out features, and in the end, the last one is giving us, right, and then there are 150 times this got printed because that's how many times it is actually running. But that does not mean that anything changes here, of course. So the summary remains the same. Uh, Now to run this code, and let me change the log file number. And how I'm testing it is I've gone ahead and put some, random images from the test values over here. So if you look at this, so this is just the images coming up, right? So I'll just quickly get rid of these. So these are the images that came up for the test, and images 1 to 10. Okay, so yeah, so how many do I have here? When it is showing me 7 of 12. Okay, and all of these I've just randomly shuffled them and put them in this list. So quickly to go and see the results, I have not, these results need to be more intelligent, so to say, uh, because going and manually seeing it is a botheration, but still, just to see the results. And this is the, this is what I've run right now. So let's look at the label. So it is giving me first glass. Okay, image 3, it is giving me glass, which is okay. Next, not glass. So image 4, which is this, not glass. Okay. Then after that, uh, 2 glass. So 9 and 8 glass. Okay. And then not glass, two of them. So that was 9 and 8. Then image 7 and 6. 7 and 6, not glass. Okay. And similarly, the last four are glass. So what is that? 10, 1, 2, 3. 1, 2, 3 glass and 10 glass. So I have run this almost like 6, 7 times, with different combinations of this. I'm getting absolutely 100% correct results over here, right? And look at this, running for 10 epochs, and accuracy is this. This is 100% accuracy. Let's look at the other values of accuracy, what we are getting before this. So 0.96, 0.98, 99, 1, 1, right? And which tensor is this? This is basically the labels tensor. Obviously, there is a shuffle which is happening. And if I'm not wrong, I've printed the training one. Let me see. So that basically my labels of the batch that is coming through. Right, so this batch which is coming through from the train loader, these are those labels, right? And as we can see, they are getting shuffled, so which is okay. Yeah, so these are changing, they are getting shuffled, which is fine. And it says 64. So is this what? This list is 64 values. Okay, it won't work this way. Yeah, but probably. Let me. Yeah, so most probably 64 values. Okay, so that's about it for now. And let me see what other things we can get from the SimpleNet. So this is SimpleNet. This is amazingly stripped down version of whatever you want to do, and it is right. Uh, so it's not resonate. It is nothing. It is just SimpleNet. Very decent results is what I'm thinking right now. I don't know. Maybe I need to really understand how come it is giving such decent results. Uh, and rest of the things that I've been trying, they're all running out of CUDA. Something else is happening, running out of memory, and this is extremely simple. It is giving such good results. Okay.